Okay, in section 5.1, we are going to look at probability tables. So we will have a table, and we'll look at a random variable x. So this is called a random variable. And in this case, they're looking at 4 births. So in this table over here, this should include all possible situations. I'll call it all possible events, because we talked about events before in probability. So if we're having 4 births, here are all the possibilities for the number of girls. You could have 0 girls out of that 4. You could have 1 girl out of the 4. You could have 2 girls out of the 4. You could have 3 girls out of the 4, or you could have all 4 being girls. So hopefully, once we know what our event generally is, it should be pretty easy to come up with these values. Now, this side over here is the probability of each of these cases. Probability of each case. So the probability of having 0 girls is pretty small. In fact, out of 4 births, we would expect there to be 2 girls. 2 girls, 2 boys. That would be the most likely. In fact, you see, that is the highest probability, 37%. 1 girl is only 25%. 3 girls is 25%. And again, so notice there's some symmetry here. 2 girls is the highest number. 1 and 3 share the same number. And then 0 and 4 share the same number. In fact, if you were to plot these probabilities, it would look something like this. It would look like a standard normal curve, where your expected number of girls is 2, and then 4 and 0 are the least likely. Okay, now that's a lot of information. We don't actually need all that to answer this question. This question is the random variable given in the accompanying table discrete or continuous? So we did talk about these words before in an earlier chapter. So if you recall, discrete was typically whole numbers, and it's finite and countable. So finite means that there's an ending to it. Let's review continuous. Continuous is pretty much the opposite of this. So this would be real numbers. So we can have decimals. It's infinite. And it's not countable, which is to say, if you wanted to count an infinite series, you would spend the rest of your life doing so and never get to the end. So you would not want to do that. This should be pretty simple to answer. So we know that this random variable, it only has 5 values. So it's definitely countable, and it's definitely finite. It has an end, 0 through 4. So this one would be discrete. In fact, most of the problems we're going to do in this class are discrete variables. So this is discrete because there are a finite number of values. Okay, so not a whole lot new there. All of that we pretty much knew before, except for this idea of putting this in a table. So that's the new part. All right, problem 2 is going to further test us on this idea of continuous or discrete, and we'll look at a bunch of examples and kind of think about it. So the first one is the time it takes to fly from city A to city B a discrete or continuous random variable, or not a random variable at all? So time to fly from one city to another is I'll just give it to you and then we can discuss it continuous. Because you can have decimal values, and depending on what unit you use, if you use seconds, right, there's a lot of different possible answers you could get. So it might take 60 minutes and 3 seconds. It might take 60 minutes and 4 seconds. I mean, you could have literally infinite number of possibilities here. Okay, how about square footage for a house? So again, this one is going to be continuous because depending on how good my measurement tool is, I could get an infinite number of values. So I go in there with the tape measure and it's 12 by 12 and I say it's 144 square feet, but then I get some kind of laser measuring tool and it tells me, well, it's actually, this wall is 12 foot and 3 inches and this wall is 12 inches and 4 inches, 12 feet and 4 inches, and then I get a whole different number, right? And then I get an even better measuring tool and I get a different number. So you can have basically an infinite number of numbers you could get out of this. Okay, C, is the response to the survey question, did you smoke in the last week, a discrete random variable? So this one is kind of a curveball because this question, did you smoke in the last week, only has 2 possible values, yes or no. So this one is not considered either of these. So this is the one where it's not a random variable at all. In fact, this one is not even quantitative, if we remember that word. So it has no units. It's not really measurable. Okay, D is the exact time it takes to evaluate 27 plus 72 as a discrete random variable. So this question is asking if I get out a stopwatch and measure each student's time it takes to solve this addition problem, what kind of times would I get? Well, again, I already argued this. Times tend to show up as continuous because I can really parse it out to the 10th of a second, the thousandth of a second, a millionth of a second. You know, it depends on how accurate I want to be. So far all of them are continuous or not even a random variable. Here's one where finally it's going to be discrete. So the number of bald eagles in a country. So bald eagles, I'm going to count them as whole numbers. And they're definitely finite. So we can't have an infinite number of bald eagles. If I want to go out and start counting them, I will complete that task eventually. It might take a long time, but it will be done, and I will have counted each one. So this is discrete. Last one here, distance baseball travels in the air after you hit it. Again, I can argue that it depends on what measuring tool I use, so it's going to be continuous. I can measure that down to the centimeter or the micrometer. Questions on those? So I'm hoping those are pretty easy. I'm hoping when you see a continuous or discrete problem that's a pretty easy one on a test or something. Most things are continuous. Okay, let's look at 3 then. So 3 is a little more interesting. 5 males with an X-linked genetic disorder have 1 child each. The random variable X is the number of children among the 5 who inherit the X-linked genetic disorder. Determine whether a probability distribution is given. If a probability distribution is given, find its mean and standard deviation. If a probability distribution is not given, identify the requirements that are not satisfied. So we need to understand what it takes to be a probability distribution. So the first thing you're going to check is you're going to look at this table and you're going to say, are all the PX's between 0 and 1? So we learned before that all probabilities must be sandwiched between 0 and 1. So if you see any negative numbers, if you see any numbers bigger than 1, you're going to immediately throw out the whole thing and say, no, doesn't work. So if we just scan these PX's quick, They're all decimal values. They're all smaller than 1, but they're all bigger than 0. So this one would be okay. So step 1, check. All of these work. Step 2 is you're going to add the px's, and they have to equal exactly 1. So I already argued that these cases have to account for all possible events in this situation. So if we're having 5 kids, we're either going to see 0 genetic disorders, exactly 1, 2, 3, 4, or all 5 kids have the genetic disorder. So let's add these. This would be 20, carry the 2. Another 20, carry the 2. 10, carry the 1. It's 1.000. So that's exactly correct. They add up to exactly 1. So this one we would say check. So far, so good. Did everyone see how I added those up? I don't want to lose you on that. You just add these columns down and carry your numbers over, and it should add up to exactly 1.000. In fact, if we had done this on the first problem I showed you, normally I show this, but let's go back to it quick. If you add up these numbers here, you get 1.001. And in this portion of the course, if you get a 1 here, even it's the small, this is tiny, just a tiny bit off of 1, you would say, there's a problem here. Somebody screwed up. And you would actually say this is not a probability distribution. They should have checked their numbers better. But in the one we're looking at now, they do add up correctly. So we can proceed. The last thing you have to check in this is that x is a random variable. So what is x in this? X is the number of children. So whenever you're counting things, that's going to work. So when you're counting things, that will lead to a random variable. And we'll actually do that a lot. We'll actually use counts of, like in the first problem, we looked at the counts of how many girls were born. In this one, we're looking at the counts of how many of these kids have a genetic disorder. So whenever you're counting, that's perfectly fine. So check. So all 3 conditions are met. So we would say, yes, this table shows a probability distribution, A. Oh, I forgot to say, not only should this be a random variable, it should be a numerical random variable. So the example of the did you smoke last week question, that's not numerical. The answer is yes or no. It's not a number in some way, shape, or form. Okay, now they want us to find the mean, mu. And we saw how to do this back in chapter 3, or maybe it was 4, one of those chapters. But it's going to be a little different in a probability distribution. And I would argue it's actually easier in a probability distribution. So here's how you calculate the mean. So mu is equal to the summation of x times p of x. So you just take each of these x values times its probability. So it'd be 0 times 0.31, 1 times 0.155, 2 times 0.314. I'll show it down here. And then you just add up all those numbers. So you'd have 0 times its probability of 0.031 plus, that's what this sigma tells you to do, is add these up, 1 times its probability of 0.155 plus 2 times 0.314 plus 3 times 0.314. Again, I'm getting these numbers from the table. I know you can't see it right now because my paper's too too low, but these are just coming from these numbers here. Plus 4 times 0.155, and then plus 5 times 0.031. And if you do that very carefully on your calculator and add them all up, you will get mu is equal to 2.5 in this problem. There's a shortcut here. Does anyone see it? Compare this number to this number. It's exactly half, right? Now that only works, that will happen a lot, but it only happens when these probabilities are symmetric. So if you notice this, 0.31 and 0.31 are the same. 155 and 155, they're the same. 314, 314, they're the same. So this is a symmetric problem. And in symmetric problems, the mean is always half of the biggest number. That's like when I said out of girls and boys, we always expect 2. So if you're having 4 kids, you expect 2 boys, 2 girls, because it's half of 4. Because it's a symmetric problem. Okay, sigma is the standard deviation. It's a little more involved. Here's the equation. You would take, oh boy, this is involved. What's the easiest way to do this one? Yeah, let's do this. Let me show you this equation. So you sum up. This time you take each x value and square it. Then you multiply by its probability. And then you subtract out the mean value squared. And then you take a square root. So it's pretty close to this one. The difference is, instead of the x value, I square the x value. So let's see what this would look like. So I'm going to almost have the exact same line here, except for each of these first numbers will be squared now. So it'll be 0 squared times that 0.031 plus 1 squared times the 0.155, 2 squared times the 0.314, 3 squared times the 0.314, 4 squared times the 0.155, and then finally 5 squared plus, 5 squared times the 0.031. You're going to take all of that, and then you're going to subtract from it mu squared. Mu is 2.5, so minus 2.5 quantity squared. And then you're going to square root all that. You would definitely want to do this in steps, right? So get this number first, then get this number, then subtract them, then square root them. What you'd end up with is, if you do this correctly, 1.11. And they want you to round to 1 decimal, so we'll call it 1.1. Stack Crunch won't help you with this. So these you got to do by hand. I'm going to show you a simpler way to do it in another problem, and basically it involves just adding columns to this and just extending the table. You could definitely make your life easier if you did it in Microsoft Excel, and I'd be happy to show any of you that if you're curious how to do it. But I don't require Excel, obviously, so you wouldn't have to. And there's only one problem I think that it would be a pain to do it by hand, but it's still doable. Okay, let's look at problem 4. Problem 4 is going to be very similar, same steps. So first question is this a probability distribution? So step 1 is to check, are all the px's sandwiched between 0 and 1? So no negatives, nothing bigger than 1. They all look good, so check. 2, do these px's add to 1? So we'd go in here. This is going to be 12 plus 8, that's a 20, carry the 2. 10, another 10, so that's another 20, carry the 2. 5, another 5, that would be 10, carry the 1. So once again, this is 1.000, exactly 1, so check. And then 3, is x numerical? So in this one, a sociologist randomly selects single adults for different groups of 3, and then the random variable x is the number in the group who say that the most fun way to flirt is in person. So again, they're counting people. So they're counting things. So yes, check. So counting is numerical. So all 3 things check out. So we would say, yes, this is a probability distribution. And then you would use those same steps from problem 3. So I would say, see problem 3 for the steps to find mu and sigma. And in this problem, you will get 1.7. Let's see if this one, so notice this one's not symmetric, right? So this is not equal to that, and this is not equal to that, so not symmetric. So you can't do that trick of dividing by 2. In fact, if you did, look at this. 3 divided by 2 is 1.5. You'd get it wrong. So be a little careful on that shortcut. These numbers have to match. Then if you did sigma with that equation I showed you, you would get 0.8. And I provide those in case you want to practice those steps later so you can get to the same results. But 5 is the one I want to get to, and that's the one I want to spend some time on. Okay, so let's look at 5, because this is the biggest one that I've assigned. And this one, you've got 10 different numbers, so that's where it could be just a little painful. But in the past, when I could have you work in groups in class, I would have students work on this, and they could always finish it in about 5 minutes. So it's still doable. All right, so step 1, let's look at all the PXs. Oh, this is 10 births, and they're looking at number of girls again. So they're counting girls. So X is definitely numerical. All these PXs are between 0 and 1. So the first check, PX is between 0 and 1, check. 2, do they all add up to 1? I'm not going to add them, but I can tell you that they will. So PXs add to 1. Check. And then we already talked about 3. They're counting number of girls. That's numerical. Check. If and only if these all 3 things check out, will we do any math? So I wish I had one where it didn't work out. Do I have one? No, except for problem 1, which we didn't even do any math on. If any of these fail, you don't do any math. So if it says, oh, calculate mu and sigma, you're going to say, no, I'm not going to, because this isn't even checks out. But this one does. So how would we do this? So this is where I would add a column and just do x times p of x. And you just go in and you multiply across. So 0 times this is 0. 1 times this would be the same number spit back at us. 2 times this would be 0.086. Dot, 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 dot. Continue that pattern. So you're just multiplying left to right and writing the number here. Then you're just going to add up these numbers. So you're going to add down. And if you do that, you will get, in this problem, 5.075. And that would be, in this problem, the mean. Then you make another column where you do, you could do a column over here called x squared, because in the second part, we need each x squared times p of x. And with counting problems like this, x squared is pretty easy to get. In fact, we could fill the whole thing in right now without doing too much effort. 0 squared is 0, 1 squared is 1, 2 squared is 4, 9, 16, 25, 36, 49, 64, 81, 100. Now we're going to take each of these numbers times this p of x. So 0 times this would be 0. 1 times this would be 0.017. This would be 4 times, I'm going to write this one, 4 times 0.043. And if you do that, you'll get 0.172. Let me do just one more so you can see the pattern. 9 times this one, 0.113. And if you do that, you should get 1.017. And then again, you add all of these down. So from the top all the way down, you add up all the numbers. And you'll get 28.835. Now this is where you have to be a little careful. That's not the answer. Because if you remember the equation, you have to take this number and then subtract this number squared and take a square root. So sigma is actually going to be this number we just found minus your mu squared, 5.075 squared, and then you take a square root of that. So notice where this number shows up. And if you do this one, if you square this, subtract those two numbers, take a square root, and you do all that correctly, you will get this number, 1.7548. Any questions on that? How I did that? How the setup goes? Okay. All right, now it asks for the range of significantly high numbers of girls and the range for significantly low numbers of girls. So this goes back, but we saw this in several sections. Sig high is equal to mu plus 2 sigmas. Sig low is equal to mu minus 2 sigmas. And we have both those numbers. So mu is this 5075. Sigma is this 1.7548. So in one case, we double this number and add it to mu. And in the other case, we double this number and subtract it from mu. So if you do this, and I would keep all these digits so that you don't round too early and get the wrong answer. Double this, add it to this, you will get 8.585. Double that number and subtract it from mu, and you will get 1.565. Okay, then they want us to round to 1 decimal, so we'll call this 8.6 and 1.6. So up here we'd say the big number, the maximum number is 8.6, and the low number is 1.6, just from these two here. I don't want to go too fast, so stop me if I lose you. We've seen these over and over again, and we're going to continue to see them throughout the course, so that's something we should definitely box and try to keep handy. Okay, then the final thing is they ask us, okay, well, if one girl is born out of 10, is that significantly low? So any number smaller than this number is considered significantly low. Any number bigger than this number is considered significantly high. 1 is smaller than that, so the answer is yes. One girl is significantly low because one girl is below the range of values that are not significant. So the answer here would be C. Basically, these numbers form cutoffs on the number line where you have, in this case, you can only have 0 girls and 10 at the maximum. And you would say anything in here is sig low. Anything in here is sig high, significantly high. And you just plot, okay, one girl would be right here. That's clearly in the significantly low region. So that's going to be the most involved problem in the homework set. Any questions on that one? That's the big one to try to make sure you have understood because, yeah, so you want to see more of this stuff down here? Okay, so let's look at 6. 6 is number of sleepwalkers in a group of 5 people. So again, they're counting, okay, are you a sleepwalker, yes or no? So they're counting up how many people claim this. And then again, the probabilities are all between 0 and 1. If you add these up, you'll get 1.000, so everything works, so you can proceed. And I would build a table, so I would do x times px, and make a new column, and I would do x squared times px, make a new column, make a column for x squareds, and then basically it's C problem 5. It's the same steps. And I'll just give you the answer to this one, and again, you can try to get to these answers on your own so you can practice these steps in your calculator. The mean for this one's going to be 1.5. And the standard deviation, if you get everything correct, will be 1.0 after you round. Okay, 7 and 8 are the problems I want to get to because they're the ones that are really, really useful. Actually, these problems here are really useful too, but they're useful because they're going to feed into what we'll do in 7 and 8, which is mathematics that basically run insurance companies and casinos. So this math I'm going to show you here is how insurance companies will never fail. They always make money. And how casinos will also never fail because they can basically plan for what we call expected value. Expected value is called E of x, and it's equal to each x value times its probability, and then add those up. And you might recognize that formula. It is exactly the same as the mu formula that I gave you, the mean. And it's best illustrated with examples. So let's look at the first one. In a state's pick 3 lottery game, you pay $1.34 to select a sequence of 3 digits from 0 to 9, such as the number 466. If you select the same sequence of 3 digits that are drawn, you win and collect $300. So the first part says how many different selections are possible. So this actually takes us back to chapter 4, and we look at this as you have choices with repetition. So basically the way we solved these problems back in chapter 4 was we said this. Okay, I have a selection for my first number, a selection for my second number, a selection for my third number. And we said, okay, I've got the digits 0 through 9. That's 10 choices times, because they allow repetition, for my second digit, I also have 10 choices. And for my third digit, I also have 10 choices. And if you multiply those 3 tens together, you get 1,000. So there are 1,000 different possibilities for this lottery. B says, what's the probability of winning? Well, the probability of a win is there's exactly one correct sequence of these 3 digits divided by 1,000 possibilities. And if you convert that to decimal, it's 0.001. So the probability of winning is 0.001. Part C says, if you win, what is your net profit? Well, the profit is that $300 that you win, but keep in mind, you had to pay for 1 ticket to win. So minus the cost of your ticket. So if you subtract those 2 numbers, you get $299.23. Okay, part D, and this is the important part. Find the expected value. The expected value is equal to each x times its probability added up. And the x's are the payouts. So I've got a $300 payout times its probability of 0.001 plus, this is the tricky part. What's the payout if I lose? And I asked it in a way to try to trick you. What occurs in my pocket if I lose? There it is. Not quite nothing, right? I lose something, yes? So the payout is actually minus this $1.34 it cost me to buy the ticket. Now here's the second trick to this. What's the probability that that happens? Beautiful. So the probability of winning is 1 out of 1,000. The probability of losing is 999 out of 1,000, which if you convert to decimal is 0.999. So this number here is 0.999. So notice, big positive number times a really small decimal, small negative number times a comparatively very big decimal, right? This is 900 times bigger than that. And if you do this math out, you will get your expected value is negative 1.038. And you're going to round to the nearest penny. So you would call it negative 1.04. And here's what's really interesting about expected value. This says that if you play the lottery every day for your life, if you play this lottery every single day for your life, you will expect to lose $1.04 every time you play. And here's what's interesting about it. You could even win a bunch of times. You might win this $300 jackpot 10, 12 times. but you're going to lose so many times that it will average out that you lost $1 for every single time. Does this make sense? So, and this is true about every casino game you'll ever play, about every bet you place on a sporting event, every lottery you ever play, you are expected to lose. But your loss is their gain, so they're expecting to collect $1.04 from every single person who plays, and so they come out ahead. Okay, so if you bet $1.34 in a certain state's pick 4 game, the expected value is negative 104. What bet is better? A $1.34 bet in the pick 3 game or a $1.34 bet in the pick 4 game? I'm not psyched about this question. It's better if they change the numbers. Notice that this expected value is a negative $1.04. This one's negative $1.04. The difference is in the pick 4 game, there's 4 numbers instead of 3. These are the same, so neither is better. How would you know which one's better? The bigger EX is, the better. So you always want to go for the bigger number. But notice, unless you find some clever way to cheat in the casino, you'll never get this to be positive, okay? If you can find a system where it's positive, take as much money as you can get and play that system because you're guaranteed to make money. Does this make sense? So E of X being, let's write this out. E of X being less than 0 is you will always lose. E of X equaling 0 is interesting. That means you can play for free. So if you get enjoyment out of gambling or something like that, an EX of 0 means you win some, you lose some. It's going to add up to 0, so you're not really losing anything. You're not gaining, but you can play for free. E of X being positive means you always come out ahead. And I want to be careful there. I don't want to say you always win. Because you will lose some, but over a long period of time, you will come out ahead. You will make money on it. Are we okay with this idea? I really want to drive this one home because, like I said, entire billion-dollar industries are based off just this principle. In fact, we're going to look at one in problem 8 that is a billion-dollar industry, maybe even more. That's insurance. And we all pay into it. And you're basically just paying down. You're basically paying in to mitigate risk, the risks of life. And you're guaranteed to lose the money. So you're basically not going to come out ahead, but in the rare case of a derecho or something, it's probably good to have it. Okay, so there is a 0.9988 probability that a randomly selected 32-year-old male lives through the year. A life insurance company charges $194 for ensuring that the male will live through the year. If the male does not survive the year, the policy pays out $80 grand as a death benefit. Complete parts A through C. The value corresponding to surviving the year is what? If you survive the year, I'm going to go a little quick on this because we're running out of time. If you survive the year, good for you, but you're out $194, right? So you paid your money, it's gone. But the nice thing is you lived. What's the value for not surviving the year? So not surviving, your family gets 80 grand, but you still had to pay for that year. Otherwise, they would not pay you the 80 grand. So you're still losing that 194. So the total profit is 79806. If the 32-year-old male purchased a policy, what is the expected value? So again, expected value would be equal to, he's got, in one situation, a loss of 194, and the probability of that is very high. It's this 0.9988. Plus, there's a probability that his family gets this 79806 times its probability of So to get this number here, you would take 1 minus 0.9988. And if you do that, you get 0.0012. So and a good check on these is the big number is always paired with the smaller number. The smaller number is always paired with the bigger decimal. So 99% chance he lives and loses $194. 12% chance he passes, actually not even 12%, 0.12% chance he passes away and his family collects $79,806. If you multiply these two and add them up, the expected value is negative $98. Can the insurance company expect to make a profit from many such policies? Why? So, of course they make a profit because they're going to their average. So if you're losing $98 on average, they're gaining $98 on average. So notice their expected value is positive. In fact, it's a pretty big number. So imagine the millions of 32-year-olds they insure. They're getting $98 from each one. Well, that's $98 million a year that they're. And again, some 32-year-olds are going to die and they're going to pay, but most of them are going to live, and they're going to collect their $194, and everybody's happy. Okay, so can't stress it enough. Expected value, hugely important in our lives. Let's finish the last two here. They're just word problems, vocab problems. So a blank random variable has either a finite or countable number of values. That's our classic discrete. So when it says finite, countable, that's discrete. And then the last problem in this section is the opposite of discrete, which is infinite many values. We called that continuous. Any questions there? That will complete section 5.1.